Okay.
Okay.
All right. Hey everyone. Today we're going to present about learning to judge a dynamic scoring function of a lifelong navigation. Our team contains of three members. We have Anne Pham, Mira Sad, and Milo Wilson. The motivation and the problem that we indicated, it was mobile robots operating in a cluttered and dynamic environment must balance safety, efficiency, and adaptability, the requirement that traditional planners often struggle to meet. Lifelong learning for navigation, which stand for LLFN, improves performance by combining a classical planner with a learned policy, but its decision making still relies on handcraft scoring, and this problem is tightly turned to DWA and fails to generalize when conditioning environments or planner change. This limitation motivation our core question: can a learned scoring function make a better attribution decision over time? From the LLFN, which is the lifelong learning for navigation, there's two controller, the classical planner and learn policy. A scorer decides which action to execute at each step. Limitation, there is a limit. So it operates by pairing two complementary controller, a classical planner and a learn policy, while a scorer selects which action to execute at each time step. However, the original LLFN scorer is manually engineered and tightly depending on the DWA internal structure, limiting its flexibility and generalization. To address this, we propose learning a neural scoring function, which is the scoring function D subscribed BSI evaluated at a state S and action of A. That evaluate state action bears directly, making attribution planner at that stage. Our approach integrates this learned scholar with granted episthetic memory, which is the GEM, to enable continued adaptation, and we validate its effectiveness through experiment score multiple 2D words or navigation environment. The stimulation steps and the environment for this. In our 2D stimulation setup, a different drive robot equipped with LIDAR, like range sensor navigates among rectangle and circle obstacle. We evaluate performance across three fixed environment types: easy, narrow passage, and cluttered, that offer increasing level of difficulty. Each episode began with a random start and a goal position placed in the different corners of the map, and the robot must reach the goal within a specific tolerance and set up a step limit to succeed. The robot's motion follows realistic kinematic constraints, including bounded linear and angular direction, and discrete time update, ensuring that the evaluation reflects practical navigation challenges. Our system combines a lightweight classical planner, which symbols candidate linear and angular, stimulate them for a short horizon, and score them based on a goal progress and obstacle clearance. In a Beller, the learned policy propose alternative action conditioned on the sensor reading and the goal at each time step. Both controllers provide action candidates, and an attributed must decide which one to execute. Instead of relying on the original handcrafted system, we introduce a learned scoring function that evaluates each state action bear directly, enabling for more flexible and data-driven attribution. Our scoring model takes as input the robot state, consisting of LIDAR readings, which is the measurement and relative goal direction, and an action represented by normalized linear and angular velocities. A lightweight MLB with a small number of a hidden layer produce a clear uh, score indicating the expected goodness of each state action pair. To train this model, we collect labored examples by performing short horizon rollouts and evaluating progress, obstacle clearance, and collision, then refine these labels using the final episode outcome. To support continued adoption across the environment, we integrate the GEM, which stores example from each word and the broader gradient to prevent forgetting, ensuring stable lifelong learning. And I'm going to pass it to Anne.
Oh, thanks, Myra. To evaluate our approach, we compare against a couple of baselines. The first is the DWA only, where we run just the classical planner. The second is the LLFN with the original heuristic scorer. And lastly, we have LLM, and then our method is the LLM with the learn scorer, optionally combined with the GEM for better continual learning. We focused on several metrics. The main one is the success rate, the fraction of episode where the robot actually reached the goal. We also look at the average number of steps required, since a path can be successful but unnecessarily long. In addition, we track collisions per episode and the number of recovery behaviors triggered, which tell us how safe and stable the navigation is. Finally, we measure the arbitration ratio, which is the fraction of the executed action that comes from the learned policy versus the classical planner. This gave us the insight into how much the system ultimately trusts the learned controller when guided by our scorer. With these metrics in mind, let's look at how the system actually performs. Next slide, please. Can you help me make to that? Okay. All right, thank you. Over the course of training, we run roughly, next slide, please. Mira, okay, thank you. Over the course of training, we run roughly 400 episodes across all 3 environment types. With the learn scorer in place, we observe a training success rate in the mid-70 range, and the collision rate per episode is relatively low. The average number of steps is reasonable given the environment complexity. One interesting pattern is the arbitration ratio. Early in the training, the system relies heavily on the classical planner, but as the scorer improves, it begins to allow more action from the learned policy. The final arbitration ratio stabilizes at a moderate level, indicating that the scorer is learning to selectively trust the learned controller rather than blindly favoring it. On a separate test set held out trials, in the easy, narrow, and clutter worlds, we see a success rate around 70%. Episodes generally require fewer steps to reach the goal compared to the distribution seen during training, which suggests that the learned scorer is steering the robot toward more efficient paths. Collisions are mostly concentrated in the clutter and narrow passage maps, which is consistent with the increased difficulties of those layouts. Overall, these results indicate that a learned scoring function can indeed improve arbitration's quality over the original heuristic. Next slide, please. Okay, let's briefly reflect on what's working and where the limitations lie. On the positive side, the learned scorer gave us a more flexible, data-driven notion of action quality than the handcrafted heuristic, because it depends on the state and action. It's not tied to a specific internals of the DWA light planner. In principle, that makes it easier to swap in a different classical planner or even multiple learned policies in the futures. The integration with GEM also helps. As we train across different environment types, GEM's gradient projection reduces the catastrophic forgetting. we can maintain reasonable performance on earlier layouts, even as we introduce new ones. On the limitation side, collisions are still non-trivial in the most challenging maps, especially the cluttered and narrow environment. Our labeling strategy, which starts from the short horizon rollouts and then adjust based on episode outcome, can be noisy and sometimes ambiguous about the action truly caused the failure. Finally, everything here is in a 2D static simulation. We don't yet handle dynamic obstacles, sensors noise, or the many practical issues that arise when you deploy a real robot. So these results are promising, but there is a gap to bridge before that real world deployment. Now let's go to the conclusion and future work. To conclude, we set out to answer whether the learned scoring function could replace the handcrafted heuristic used for arbitration in LLFN. Our experiments suggest that the answer is yes. A neural scorer over state action pairs can achieve good success rates, maintain relatively low collision rates, and guide the system to selectively trust the learned policy in a way that generalizes across multiple environment types. Looking ahead, there are several directions for the future work. We like to design a richer state representation, for example, by including an explicit occupancy grid or short action history. We also like to develop better label and rewarding scheme that are more sensitive to collision and long horizon performance, rather than relying on our current approximation. The next big step would be to move from 2D simulation into more realistic 3D simulators or real robots, and to introduce dynamic obstacles and sensor noise to stress test the scorer. Finally, we're interested in comparing this arbitration approach against other navigation stacks and decision-making architectures. Thank you for your attention. We'll stop here, and we're happy to take any question over the discussion. Thank you.